Uh, Hello, this is a video demonstration for E533's Lab 11, which is about uh, integrating multiple threads in our previous single core RISC-V processor. And we will be making all these individual, like four threads, working on the network packets and see how like we manipulate stuff. We apologize, the video is pretty late, so let's get started. So onto the RISC Verilog. To make it multi-threaded, we had to have multiple PCs and a thread selector. And the thread selecting logic is based on round robin scheduling. So like every thread will have its turn one by one. So it goes like thread 0, then thread 1, 2, 3, then again the same thing, thread 0, 1, 2, 3. So here I go top. Here we have defined that this is the thread state, so thread 0, this for thread 1, likewise. And since there are multiple threads, we got to have different PCs and have the start address pointing to different instruction memory addresses. So uh, depending on our assembly language, when we generate it from the compiler, the binaries, which we feed it to the COE file, and it gets coupled with the our IP core of the data instruction memory, we need to give the addresses uh, so that every thread knows which instruction it has to execute. So, as you can see here, we have all the threads have their own PCs, and it goes to a muxing logic. And since we have four threads, so they are like through two select lines. So if the select line says 00, the PC for thread 0 gets selected, and instruction memory is addressed, and the instruction is decoded after that, obviously being fetched. Uh, so I'll show you the logic. So yeah, so assign the current PC. So if the thread state is at 3, assign the PC of thread 3. If it's thread state 2, then assign thread two's PC. Same goes for this thread. It's the thread 1 state, then thread 1's PC, and then we are left at, if none of them, if the state is neither 3, 2, or 1, then the PC has to be issued of thread zeros. Okay, moving on. So basically, this statement translates it to a 4 is to 1 mux logic. So here we have like four PCs, but coupled with the mux logic. But here we are only using one register of having only 32 registers. So we have hard coded that these like when we go to the assembly program, we'll see that we are using a couple like certain registers for only that specific thread. So moving on. So this is the assembly program, how it looks like. But before this, I would like to show you what is our protocol. So like we have implemented it. We have implemented a what is intercommunication between the threads. So here you have our FSM, and this is how, I mean, it governs the exchange between the data, like between the NetFPGA and our code, and that's how they take turns to access the data memory. So here we have four states, so like start, payload, CPU process, and read ready state. So yeah, here's a Verilog code for this. So it's pretty simple. So like if the fall through small FIFO is not empty and the output is ready, we go to the payload state, and also like if the info control is not zero, so where, like this the 8-bit control signal, if it's not zero, then it is definitely a payload, and this header is attached, like it's been attached by the NetFPGA. So we go to the payload state, and when you go to the payload state, so yeah, the same thing, false or small was not empty and output ready. And we have the signal call NP for write messenger next if it's one. And again, the infi for control signal is non-zero. We head to the CPU process state, and this is where our process threads and the core interacts with the data and all the load store things again. And when and the last state, so like from CPU to ready state, when the threads are done working, uh, there's a signal called CPU job complete, and when it goes high, we go to read ready state, and also we check for the read pointer and write pointer when the CPU done state, CPU job complete is high, so that we increment the read pointer, and then we move over to read ready state so that the data can go through the downstream. Moving on, let's check out the assembly code. So here we have one master, like four threads having inter-thread communication. One thread, which is like thread zero, is like acting as a parent thread, and the other three are like child threads. So the job of the first thread, the thread zero, is like kind of like managing all the rest of the threads. So it's actually checking the packet, and if seeing if it's a UDP protocol packet, then it will let the other threads work on that packet. So thread one, what basically is doing is it is making the checksum zero for the IP datagram. Thread two is making the checksum zero for the UDP header, and thread three is making manipulating the payload. So we'll be going over how what data actually we are sending and what we receive. So we use a couple registers to initialize value, and there are like certain loops. So we are continuously checking if it's in the CPU state. If it's in the CPU state, then we load the we load the location from the lead pointer, and we load the data into our registers and see if it's a UDP packet or not. So how to the identifier for the if it's a UDP packet is actually 1711 in hex. So if this branch condition is true, then the thread zero updates the status to the other threads, and they can start working on it. If it's not, if the branch fails, it'll again jump back to job complete, because uh, it could be another packet like TCP or ICMP or something. So if we don't jump back to job complete, then the state machine will get stuck, and we would never go to start again or even any other states. So and yeah, like if it's a UDP packet and other threads are working, the thread zero, it needs to continuously listen whether the other threads, the child, they completed the have they completed their instructions, executing all the instructions successfully. So it keeps on hearing till this branch condition is successful, and then after this the state changes from the CPU, the state 3 to state 4, which is the read ready, so the data can flow through the downstream. uh, so here it is, thread 1 instruction, as I said, it's making the checksum 0, and for thread 2, for UDP, it's making the checksum 0, and for thread 3, we are issuing like we are manipulating the payload and making it write hello Garcia. We'll see how it is in the uh, when we extract the data from the logic analyzer. We'll see how it translates. So all these threads, when they're done, they need to check. They need to communicate the status. So how we have done is like uh, thread 3 will put 164 value in T6, and then thread 2 will put 163 value in S7 register, and then thread 1 will put 162. And the job of the thread 0 is to check the sum. So like all these 161, 162, 164, they add up to 489. So it has to check. So branch equal T1 to T0. So if it is, then shop complete. All the threads have done their job. So it can again rinse and repeat. Yeah. So having all this, we generate the bit file, and then I mean I just went ahead and uploaded the bit file and emulated the design onto the NetFPGA using on the DETERLab. So here it is. I would like to mention that we upgraded, the past logic analyzer, and you know, actually we call it the logic thief actually, and I would like to dub it like this is a logic heist because what we did was basically we are capturing each and every possible data, so like the thread ID, state, the PC, the read address, everything, and even the data obviously. So this really helps in uh, analyzing how at what steps, and it's like a deep inspection kind of thing. So it really helps give us an idea of what's going on, and I think it's highly useful in debugging and did save a lot of time. So here we did the so here we use the socket programming, and onto the we are sending data from node 0 to node 1. And this is the port number is 1234. This is the IP for it, and the message here we want to convey to node 1 is hello Mumbai. Uh, and when we went and ran a logic analyzer, so this is the data. So you can see. So let's focus on the first one. So FF, these are the 8-bit control signal. So this is for so this means this the NetFPGA's 64-bit header, and this is the input to begin with. So we can see. Let's go on. So there are a few things. So first we have the net. When we send a packet to it, so the NetFPGA attaches its header onto it. Then comes the Ethernet frame, and then which is of 14 bytes. Then we have the IP datagram, the UDP segment. Then finally our payload. Uh, so 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 what I'm gonna do is I'm gonna log each and every data so that we can have a good clarity how the input data was, and then what our single core multi-thread network processor did to manipulate the what we intended. So what our assembly did, what our processor did wanted to do was make the force the checksum to 0 and manipulate the payload. So let's go. So the first one is like FF. So this means this is the NetFPGA header, the 64-bit header. So now onto the destination mark. Uh, so this is the Ethernet header. So this first 6 bytes are the destination address, and the later 6 bytes are the source, and that after that comes the length. All right. So I went ahead and mentioned what is the sizes of each and every parameters. So like destination MAC is for 6 bytes, and the Ethernet freedom and so and so and so. So so the NetFPGA header, I've just gone ahead and copied. So like this is it. Then begins my Ethernet frame. So yeah, so this is the high data and this is low data. So 64-bit data. So but we have our hardware and software registers, they're like 32 bits. So hence, so destination mark is 6 bytes. Okay, so let's go ahead. All right, that makes up 6 bytes. Now, right, and the type is 2 bytes. So this is the type. Mhm. So now from here the IP datagram begins. So the first one is the version. So you see it's a 4. So yeah, this is actually IP version 4, IPv4. Hence the 4. Then comes the Helen. Again the bits says fine. Let me do this is much better. No, I will also. Okay. And then comes the service byte. Here it's just plan 0. Right. Uh, 0 0. Right. And then the length. Length we have staying. And then is the identification. So that's another. So I'll just type it. That's 90 40, right? And then I have the flag. It's like 3 bits. So it's probably just 0. And the fragmentation offset. So it's 003, right? And then I have the TTL. It's 0A. And so here this last byte is 11 and it corresponds to the protocol. So 11 and 11, this is an hex, translates to 17, it means it's UDP protocol. Then comes the header checksum. So it's for like 4 bytes. So the whole thing. And it's my source IP. I'm sorry. This is 2 bytes. Here our source IP. And destination IP. So yeah, and now from here the UDP segment starts. So and as we can see, the UDP length says it's 16. That means our packet, I mean, like our payload is actually 14 bytes. 14 plus 8, so 22. So that's what it says, that UDP length is the size of the payload and the UDP segment header. And what's the last thing? Yeah, the last two bytes are for the checksum, and we will be emphasizing on this because according to, like, our core should force this to 0, and when we go, like, how the packet has been flown to the downstream, how it looks like. And yeah, not to forget the payload. So this is the payload. So actually, if I go ahead and copy this whole thing and convert it to ASCII, I actually have done this before. So let's say, so yeah, it says hello Mumbai. So this is our input message. So yeah, so as you can see, as soon as we get the whole packet, like let's focus the state. So the state one was start, and then we jump to the CPU mode actually. So that, which is our state 3, and now all the threads take turn, and then they execute the instructions, and till we have our output when it's finally manipulated. So actually, so this is the read data where we are probing from the downstream using a logic heister. So here we can see this is the read output. We can see its state is at 2, which is the read ready state. So like CPU, it was done working, it was like state 3, and then now it's read ready state, and the data is going to the downstream. So again, the same thing. The 64-bit NetFPGA header remains intact. Then comes our destination MAC, which is like 6 bytes. So 4 bytes here, 4 bytes there, 2 bytes there. It is intact. Moving on. So source MAC also same. And then as we can see, the type is also 088800. There you go. Now from here, the IP datagram starts. So 45. Let's put it down. Version IP 45. Length is 5. Then is the service type 00, same thing. The length to ABS, the length remains the same. 90 identification is also pretty much the same. The flag is 0. The fragmentation offset is also 004, 0, same thing. Then protocol is still the same, 11, which is UDP. Uh, right, yeah. So now the interesting part where we see our net processor working. So after the protocol comes the IP header checksum, and remember the IP header, like thread one was the one was forcing the checksum for the IP header. So we can see just after the protocol, the 2 bytes of the checksum has been forced to 0. So this is the change. Source IP remains the same as the destination IP. We haven't manipulated the destination IP. Moving on to the UDP segment from here. Same source port remains the same, B315, destination port same, UDP length 0116 same. Here the checksum for this has been forced to 0 by thread 2. And now comes our actual payload. So this is what the message is like. Let's go ahead and copy this and see how it looks. 20. And I'm gonna go ahead and convert this to ASCII. And it says, as expected, hello Agursa. So this demonstrates that our single core 4-threaded RISC-V processor is capable of acting as a network processor and is able to manipulate packets successfully. Thank you.